Hello everyone, welcome to worked example 5.15 on page 218 in the section 5.2 heating effect of electric currents. Look at the circuit below. Determine the current in the 2 ohm resistor and the potential difference across the two marked points A and B when the switches A opened and B closed. So we have two scenarios, A open switch. And in both these cases, we have to find the current here, and we have to find the potential difference across these 2 points. All right, so in order for electricity to flow through a circuit, there has to be a closed path. And so if you start your car here and you want to end up on the other side, so if you start on the left, you want to end up on the right, you have to be able to drive in some kind of closed loop. Right? So if you only go through one path, for example, if this part was not here, if you only try to go through this path, you've got a break in the road. You can't travel. And so all the traffic along the road stops. But in this case, we have another road. So while we cannot turn right here, we can go straight and pass through this toll booth. And then we have a decision whether we're going to go through toll booth on the top or the toll booth on the bottom. But the idea is the current will still travel. So we've got the negative side, positive side. We know by definition the conventional current comes out of the positive side, unfortunately. I keep saying that because it really is unfortunate, but it's what we're stuck with. So when it's open, okay, we've got the current going through the 2 ohm resistor. It comes to this junction and then it splits. Now, because each of these resistors is identical in terms of its resistance, the current will split evenly. So half of it will come here and the other half will come here. Okay? Then the two halves join at this junction into the original current and they come back to the source. All right, so we have to find the current in the 2 ohm resistor. Whatever current comes out of the battery, which is the total current, notice that that's the same current that goes through the 2 ohm resistor. So I1 is equal to I total. And in order to find I total, I would use Ohm's law. V is equal to IR. Rearrange that for current, so that's V divided by R. And specifically, since we're looking for total current, we'll call that total voltage divided by total resistance. Now your total voltage is 12 volts. And your total resistance, that's something we're going to have to work out to find, right? So looking at this, I've got these two resistors here in parallel. So why don't we do this? Why don't we call this resistor 1, this one will be 2, and this one will be 3. Right? I always want to number them. So I'm going to merge resistors 2 and 3, and I'm going to make them into a single equivalent resistor. So let's merge these two right here. So we're going to make R sub 2, 3. Now, I'm not going to draw what the new picture is going to look like. Just know that it's going to be equivalent to having just the one resistor. So R23, because it's in parallel, well, because they're in parallel, 1 over R23 is equal to 1 over R2 plus 1 over R3. So that's going to be 1 over 4.0 plus 1 over 4.0. So 1 divided by 4 is a quarter. That's 0.25. Or you could do it like this. You could say, well, they have a common denominator. So 1 plus 1 in the numerator makes 2. 2 divided by 4 is equal to 1 over R23. So therefore, R23 over 1 is equal to 4 over 2, which is 2. Okay, so the equivalent resistance of 2 and 3 is 2 ohms. All right, so what does that mean? That means this resistor would be in series with R1, which is 2 ohms. And if these two are in series with each other, how do you find the equivalent resistance? Well, you would simply merge them together. So if we take R1 and we add R23, we'll have R123, also known as the total resistance. All right, so RT is equal to R1, which is 2 ohms, plus R23, which is 2 ohms. So the total resistance in the circuit, or the equivalent resistance, is 4 ohms. So we're going to plug that in over here. Okay, so we were looking for total current. So 12 divided by 4, that's 3. So 3.0 amperes. Okay, so that is the current that is going through the 2 ohm resistor, because like I said, the total current and the current through 1 are the same. So we can say, therefore, the current through the 2.0 ohm resistor, when the switch is open, is 3.0 amps or amperes. Okay, so there's our answer, well, part of our answer for part A. Now we have to find the current in the 2 ohm resistor and the potential difference across the two marked points A and B. Well, notice where A and B are. A is across from this point in the 2, and B is across from this point in the 2. Remember I said that when you have resistors that are in parallel, they have the same voltage drop. They have the same potential difference, regardless of whether the resistances are or are not the same. So whatever voltage drop we have here, this will have the same. So V2 equals V3. And that's just because they're parallel. So these 2 points in the circuit have the same voltage, and these 2 points in the circuit have the same voltage. And I'm pointing to specifically points just before and just after each resistor. And so therefore, the difference between those 2 points also has to be the same. Now, point A, I mean, this corresponds to this point up here. Let me use a different color. Point A corresponds to this point on top, so I'm just going to call this A prime. And point B corresponds to this point up here, which is B prime. So the question really is, what's the voltage difference between A prime and B prime? That's going to be the same as the voltage difference between A and B, because they're exactly parallel to each other. So the voltage drop between A prime and B prime is the voltage drop across resistor 1, and that's going to be V1. So I got to find V1. Okay, now how do I find V1? Well, using Ohm's law. So V1 is equal to I1 times R1. And I1, I already stated, it's equal to the total current, which is 3 amps. And that's times the resistance R1, it's in the picture, 2.0 ohms. That's 6.0 volts. All right, so I have 6 volts of potential difference between points A and B. So that's the other half of part A. So therefore, the potential difference across points A and B when the circuit is open is 6.0 volts. All right, so that is our solution for the open switch. Okay, so now let's see, well, how is this going to change or maybe not change if you have a closed switch? Well, remember that anything in life, whether it's a particle or even you one day in your car, you want the path of least resistance. So if that switch gets closed, this is all of a sudden a new road or a new path for the electrons that they can take. So the electrons, again, assuming unfortunately they come out of this side of the battery, they get to this junction. Now, would they really want to split? I mean, do half of them really want to go through an extra resistance here, whereas here, none of them would go through any resistance? Well, they would all take this path because this is the path of no resistance. All right, so we have all the electrons now, so they're coming out of here. They are going through this path because now we're assuming the switch is closed. Okay, so they're coming through, and they get to this junction, which is at point B. Now at this point, they have no choice. They have to go through at least resistor 3, which is 4 ohms. So half of them are going to come here, and the other half are going to go here to resistor 2 because they can split, right? So all the cars had no traffic. All of a sudden here, there's traffic. So half will go here, half will go here, one into each lane. So we have I total that gets to this junction. Half of it comes here, and the other half, like I said, splits and goes to the top. Those two halves rejoin and then come back to the battery. Okay, so we're looking for the current in the 2 ohm switch. Well, take a look at the picture. If the switch is closed, the electrons are not even going to bother going through the 2 ohm resistor. And if that's the case, that means the current in the 2 ohm resistor is going to be 0. So, but we have to explain this. We don't just want to state it as is. So this is what we'll say. With the switch closed, there is now a new path with 0 resistance, comma. So all the electrons will forego the 2 ohm resistor and take the new path. Okay, so since no electrons pass through, oh, I apologize, guys. Since no electrons will pass through the 2 ohm resistor, I1 equals 0 amperes. All right, it's just pretty logical. Nothing's moving through, there's no current. All right, so that's the current, and now what about potential difference? Well, remember that, okay, well, what's the point of potential difference? There's some voltage before you get to the resistor or the object that's using the electricity, and there's some voltage at a point after. Now, the whole point of finding potential difference is to find a voltage difference. Before the resistor, there's a somewhat higher voltage, and then after some voltage gets used up here, there's a slightly lower voltage on the right. So when you find the voltage here and you subtract from it the voltage here, you get the change in voltage, right? Delta V1, which is sometimes just called V1. A lot of times we just don't draw the delta, the change symbol. But if no electrons are going through there, right? So if all the electrons are going through here, and keep in mind the potential difference between A and B, now we're considering these 2 points, there's nothing between points A and B except conducting wire. And so there's nothing to cause a resistance, there's nothing to use up any voltage, which means whatever voltage I have at point A, I have the same voltage at point B. Now, if you're thinking, well, the only way to use that voltage is to have resistance, and the electrical wire does have some resistance, you're right. In reality, the electrical wires do have resistance. They are not perfect, conductors. However, for our purposes, we assume that these conducting wires are ideal wires of 0 resistance. In other words, the voltage here is equal to the voltage here, giving us a voltage difference between A and B of 0. So that's what we're going to say. Between points A and B, excuse me, no voltage is dissipated or lost, as there is no medium with resistance between points A and B. And in brackets, we're going to say, we assume the conducting wires to be ideal wires of 0 resistance. Therefore, delta V between points A and B is equal to 0. And if you want, you can stick the volt symbol there as well. All right, so that is the end of worked example 5.15.